Hello, wonderful people. Here we are, chapter 32, Electrostatics, and this is section 4. Now, this is not going to be a part of my permanent lectures because I found out this morning that this section was messed up. So I'm re-recording this just for period 4, and then I'll fix this again for next year. So here, let's just electrostatics. That's electricity at rest, which just means electric charges are sitting right there. I like this picture. So the enormous attractive and repulsive electrical forces between the charges in the earth and the charges in your body balance out. So if you had all the protons in the earth and the electrons and the protons in you pushing each other apart, it would push you up like this and you would launch off the earth's surface. But if you had all these protons, but you have protons in you and you also have electrons in you. So the electrons are pulling you down with the same force. So those forces cancel out. And then if you just count electrons in here, well, it's the same thing. There's electrons in here, which you push you up, and protons, which pull you down. So the end result is all those electrical forces, because there's positive and negatives, and some attract and some repel, they all cancel out. So you just sit there on the surface of the earth. So if the electrical forces aren't going to push you up or down, what's left? Well, gravity. In comparison, gravity is a small force, but that small force is what keeps you stuck to the surface of the earth. I can shorten that up, but there's the long answer. How can I say that short? The charges balance out, and then you just have gravity left over. Another way to look at this is here. Sometimes charges repel, sometimes they attract. Are they the same or alike? But gravity always attracts. There's no such thing as anti-mass that's going to push you away. So as soon as you start getting more and more mass, you get more and more gravity. That's not always the case with charges, because if you have a positive charge and then you get more positive charge, well, they're going to push apart. But if you also get negative charge, they're going to pull together, and you can make them cancel out. So this was in yesterday's homework. There's the equation for gravity. There's the equation for electricity. Here we count how much charge there is. Here we count how much mass there is. And then new for today, 32.4, conductors and insulators. Electrons move easily in good conductors and poorly in good insulators. So we're going to talk about that and some of the why that is. Outer electrons of the atom in a metal are not anchored to the nuclei of particular atoms. They are free to roam around in the material. Materials through which electric charge can flow are called conductors. Metals are good conductors for the motion of electric charges because their electrons are loose. Do I have a picture of that? No. I will next year, but for now I don't. So what's the point? The point is, in metals, there's extra electrons that are free to roam around between the atoms. Electrons in other materials, such as rubber and glass, are tightly bound and remain with particular atoms. So there's no extra electrons. Every electron is tightly bound to its atom. They are not free to wander about the other atoms in the material. And these materials are known as insulators. And they are the opposite of a conductor. So they are poor conductors of electricity. A substance, any substance, is classified as a conductor or an insulator based on how tightly the atoms of the substance hold their electrons. So the conductivity of a metal can be more than 1,000,000 trillion times greater than the conductivity of an insulator such as glass. In power lines, like shown hanging here, and heck, you can see them all over town, charge flows much more easily through hundreds of kilometers of metal wire than through the few centimeters of insulating material that separate the wire from the supporting tower. You don't see it real good in that picture. I'll make this better for next year. Now, we've talked about conductors and insulators. What about materials that are halfway between them? Well, here's the word, semiconductor. The word semi means half. So they could have called it a semi-insulator, but they didn't. They chose semiconductor. Are materials that can be made to behave sometimes as insulators and sometimes as conductors. Atoms in a semiconductor hold their electrons until given a small energy boost. So there's examples of it. I'm not going to worry about that for now. What is the difference between a good conductor and a good insulator? A good conductor has electrons that can move freely through the material. And a good insulator, all the electrons are tightly bound to the atom, so there's no electrons to move around. And that's that. Okay. That will be enough to get you through the homework. I do not address superconductor, so if I forget to remove the superconductor question, just skip it. Thank you.